Today, we're going to be learning about partial fraction decomposition. So, you know how when we want to add fractions, we have to make both fractions have the same denominator. So, in this case, I'm going to multiply by d on the top and bottom here, and b on the top and bottom here. So we have, this is ad plus cb over db. Partial fraction decomposition is going from here to here instead of here to here. Like the last example, if you want to see the partial fractions, then we have to rewrite the denominator so that we can see the multiplication. Notice that we can factor the denominator into x plus 2 times x plus 3. So now, in this form, we can make the conjecture that this fraction must be the result of adding something over x plus 2 and something else over x plus 3. And the reason we can say this is because if we want to add these fractions again, we have to get the least common multiple of the denominators, which in this case is just x plus 2 times x plus 3. And so since that is our denominator here, we can make this conjecture. So now I have an equation in terms of x, a, and b. Now what I have to do is just solve for a and b. I'm going to start by multiplying both sides by x plus 2 times x plus 3. And doing this, that cancels the denominator on the left, and this turns it into a times x plus 3, because the x plus 2's cancel, and b times x plus 2, because the x plus 3's cancel. Now I have this expression, and from here we can selectively plug in values of x to find out what a and b are. Right now I have 3 unknowns, and by plugging in a value for x, we'll reduce it to 2. But if we want to get an actual number for a and b, we have to make a substitution such that plugging in the x also gets rid of a or b. And we see that we can either do x equals minus 3 to make this 0 and cancel this out, or x equals minus 2 to make this 0 and cancel this out. We just have to test both cases to find a and b. I'm going to begin when x equals negative 3. So in this case, the equation turns into 1 equals, so minus 3 plus 3 is 0, so this goes away. And here, b times minus 3 plus 2, which is negative 1. And from here, we can see that b equals negative 1. In the second case, when x equals negative 2, then we have 1 equals a times minus 2 plus 3, and then this goes to 0. So minus 2 plus 3 is 1, so we have a equals 1. Now, all we have to do is take these values and then plug them in way up top. So we found a equals 1, so this becomes 1 over x plus 2, and b equals negative 1, so this we can turn into a minus 1 over x plus 3. And this right here is the partial fraction decomposition of this. More generally, if we have something over a product of linear factors, then the partial fraction decomposition is in this form. So in another case where instead of just linear factors, we have a quadratic factor here, then our decomposition has to evolve to reflect that. And the rule we want to follow is the top should be 1 degree lower than the bottom. So what that means is here I have a linear factor. So when this linear term is in the denominator, it's degree 1. So its numerator must be degree 0, which is here. And same for this. But here the quadratic is a second degree term. So we have a quadratic on the denominator. So we must have a linear on the numerator, like so. But you should keep in mind, this second case is not in AP Calculus. And in a case where instead of unique factors, there's one repeated factor, then instead of just doing the one factor, we have to do it for every number of n up to n. Now you've learned how to perform partial fraction decomposition, we're going to apply that skill by using it in integration. To practice, we're going to use this integral as an example. First thing you should always try to do, and what I'm going to try, is I'm going to try u sub. So I'm going to try to let u equal the entire denominator, or x squared plus 9x plus 20. And after differentiating, we see that du equals 2x plus 9 dx. But if you notice, Up top, we have 2x plus 3 dx, and there's nothing we can multiply as a coefficient to make this top equal 2x plus 9 dx. So we have to do another way, and that way is partial fraction decomposition. Okay, so notice that I can factor this quadratic in the denominator to x plus 4 times x plus 5. Knowing that, we can rewrite our problem like this. And here we see that this denominator is the result of adding something over x plus 4 and something over x plus 5. I'm going to mathematically express that in this equation. So now what I'm going to do is I'm going to multiply both sides by x plus 4 times x plus 5 to get rid of all denominators. And that gives me this, because when I multiply by x plus 4 times x plus 5, this denominator cancels to leave 2x plus 3. Here, the x plus 4's cancel to leave x plus 5, and here the x plus 5's cancel to leave x plus 4. So remember, we want to pick our values of x such that it also gets rid of one of these a or b. And here we can see that there's two possible values we can try for x. We have x equals minus 5, which makes this go to 0, and x equals minus 4, which makes this go to 0. And this is what I get when I plug in x equals minus 5. So you see here, minus 5 plus 5 is 0, so a times 0 is 0. This goes away. This becomes minus 10 plus 3 equals, so minus 5 plus 4 is negative 1, so this is negative b. So we have negative 7 equals negative b, so b equals 7. And when I plug in x equals minus 4, we get this, and minus 4 plus 4 is 0, making this term go to 0. So we have minus 8 plus 3 equals, so here minus 4 plus 5 is 1. This is just a. So we see that minus 5 equals a. And now that we found our a and b, all that's left now is just put these back in here and then substitute in our integral. Now we found that our integrand decomposes into this, which means we can rewrite our integral like this. And from here, I'm going to split into two integrals, like so. And now I'm going to pull the constants out of both integrals, like so. Side note, if you're doing partial fraction decomposition problems, you'll often encounter integrals in the form 1 over x plus c, like here and here, where c is any constant. So in this case, this is just equal to the ln of x plus c plus your big C. And this is because if we let u equal x plus c, then we have du dx equals 1, and so du equals dx. So we can make the substitution to make this into 1 over u du, which we know is ln of u, and since u is x plus c, this is just ln of x plus c plus your big C. So knowing this, we know that this is minus 5, the ln of x plus 4, plus 7 times the ln of x plus 5, and don't forget your plus c, and we're done. Okay, now we have a similar scenario, except we have a repeated linear factor here. So if you remember, the way to decompose this is we're going to have one factor for every value of n, like so. And then now I'm going to multiply both sides by x plus 3 cubed, like so. But now you'll notice if we try to use the cover-up method and plug in x equals minus 3, then that gets rid of a and b at the same time, so that won't work. So this is where we have to use a second method called equivalence of coefficients. What this means is we're going to equate the coefficients on the left side to the coefficients on the right side, and you'll see what I mean. I'm going to begin first by expanding everything on the right, like so. And so now what I'm going to do is I'm going to group all second degree terms together and all first degree terms together and all constants together, like so. See how I factored out an x squared out of all of the x squared terms, an x out of all of the first degree terms, and then I've grouped the constants together. What equivalence of coefficients means is we're going to take every coefficient on the left and equate it with its coefficient on the right. Okay, I'm going to start by considering the x squared term. So notice that on the right, the a is the coefficient of the x squared. But notice on the left, there's no x squared term, so that must mean the coefficient on the left is 0. And since coefficients have to be equivalent, this must mean a equals 0. And going on the same path, we see that the coefficient of x on the right is 6a plus b, and the coefficient of x on the left is 6. So we know that 6 must equal 6a plus b. And from this first step, we know that a equals 0, so this must mean b equals 6. Now for the constants, we see that the constant term on the right is 9a plus 3b plus c. But on the left, it's 11. So we know 11 must equal 9a plus 3b plus c. And now, using these two pieces of information that we found earlier, we can simplify this to 11 equals 0 plus 18 plus c. And we can see that c equals -7. By the equivalence of coefficients, we found all of our numerators. And now all that's left is to substitute these back here and then integrate. So with those substitutions, this is what the decomposition looks like. And since a is 0, we can actually just get rid of this term entirely. The decomposition of 6x plus 11 over x plus 3 cubed is 6 over x plus 3 squared minus 7 over x plus 3 cubed. And with this knowledge, we can rewrite our integrand into this. And like the last problem, I'm going to begin by separating this into two integrals. Now I'm going to bring out the constants, like so. And since this is x plus 3 here and x plus 3 here, I'm going to make a substitution for the entire problem. I'm going to say that u equals x plus 3. And so du equals dx. So when I make this substitution here, I get this, which I can just solve using the power rule. And this is the result after integrating. And then we can simplify to -6 over x plus 3 plus 7 over 2 times x plus 3 squared plus c. And that's how you integrate with partial fractions.